Good afternoon, ladies and gentlemen. Welcome to the Academia Sinica Lecture 2025. Before we begin, we are pleased to invite President James Liao to give the opening remarks. Please join me in welcoming President Liao.
Good afternoon, ladies and gentlemen. It's my great honor to have you here to listen to our special guest, Dr. Peter Galison, for this Academia Sinica lecture. And this Academia Sinica lecture is the most significant lectureship in Academia Sinica and is held once a year. And this year is particularly interesting because Dr. Galison is going to talk about the junction between science and humanity. And this is a topic that every one of us should be care about. However, we seldom talk about it. And Dr. Galison is one of the very few scholars that can cross between science and humanities. So I'm sure his lecture today will be extremely insightful. So we look forward to that. And thank you again, Dr. Galison, for coming to Academia Sinica.
Thank you, President Liao. Now, before the lecture begins, we would like to invite Dr. Ziqing Mo to give the introduction.
All right, thanks for the opening, President Liao. It's my great pleasure to introduce Dr. Peter Galison as the Academic Sinica Lecturer of 2025. His achievement has been so renowned, so I cannot do everything to tell you all the details of his scientific as well as humanity achievements. Just a few words before we invite him to the stage. As you know, each year we run the open house here in Academia Sinica. And in the year of 2009, the open house of Academia Sinica attract more than 200,000 visitors coming to our campus. That's the historical high peak of visitors for that event. And we invest why so many people came to Academia Sinica open house in that year. And the answer was very clear because we had the exhibition of black hole. And obviously, because of that remarkable number of people coming to Academia Sinica to see the black hole exhibition, we can imagine that human beings are so curious about the nature of universe. And the black hole is one of the hallmark of the secret of universe. And that leads to our introduction to Dr. Peter Galison. As you know, he has been leading the Event Horizon Telescope collaboration since more than 10 years ago, I guess. And our black hole exhibition was part of the Event Horizon Telescope international collaboration. So obviously, Academia Sinica and the scientists in Taiwan were so proud to be part of the event, and we do contribute significantly to the image of black hole. Dr. Galison, as President Liao pointed out, he has a very interesting career. He integrates the role as a historian, philosopher, as well as a scientist in a single person. So from his lecture today, you will see how such integrated disciplines can really make a breakthrough. And his achievement also award him a lot of international recognition. Some of them including the Pfizer Award for Image and Logic, and Max Planck and Humboldt Stapleton Prize, and Abraham Pierce Award, etc. All right, so in addition to the scientific achievement, Dr. Peter Galison also make films and documentaries. And as he just said, some of them now is broadcasting in Netflix. So you will be feeling free to explore what his team has already documented, the images of black hole. All right, so once again, the presence of Dr. Galison here shows a great role model for a single person who can integrate so many different disciplines as a whole. So before his lecture start, let's welcome President Liao coming to the stage. We have the Crystal Award to be given to Dr. Galison. And Dr. Galison, also please coming to the stage here.
Thank you, President Liao, and thank you to all the faculty, to the students I've so enjoyed meeting, to both the scientists with whom I work on the Event Horizon Telescope and the humanists who I've come to know, including Kevin Chang. Thank you all for inviting me. It's an honor to be here, and I'm going to tell you a little bit about black holes as a place where so many disciplines cross, including between the sciences and the humanities. This is an age, a golden age of astronomy. There are amazing things in the sky that we've been studying. We've been looking at dark matter, most of what's out there in the universe that we can't see. We've been looking at exoplanets, planets that we're beginning to understand that might look more and more like Earth as we're able to see ones that are approximately the right distance and distance from their suns and size. We've been looking at strange objects, pulsars, spinning neutron stars that send signals like flashing lighthouses and help us calibrate the dynamics of the universe around us. And magnetars, stars, neutron stars that have huge magnetic fields, unimaginably large. But there's something about black holes that attract our attention. Black holes are the ultimate paradoxical object. They're the brightest objects in the sky, sending beams from the very early universe as far away as could be all the way to us. They're also the darkest object. They reflect no light, they emit no light. They are the simplest objects that you could have. They're almost like an elementary particle writ large. There's very little to say about them classically. They're spinning and they have a mass, and that's almost the end of the story, at least classically conceived. But as we understand them better through quantum mechanics, they may be the most complex objects in the universe, the ultimate hard drive, the storage site for an unbelievable amount of information of everything that has light that's fallen into it, objects that have fallen into it, from photons to stars. They're extraordinarily massive. The first one that the Event Horizon Telescope imaged is 6.5 billion times the mass of the sun, and yet there's no surface. They're not substantial the way a podium is, or even an electron or a proton. And then they are a place where space and time seems to switch their roles. In our world that we inhabit all the time, we can move back and forth across space, but time seems to go in an inexorable direction, always forward. In a black hole, once you cross that horizon, you are going in towards the singularity at the center. There is no going back, there's not even standing still. So the movement through space comes to behave like our movement through time. For all these reasons and many more, in 2015, a group of us from many different disciplines, Shep Doleman on the left, who is head of the Event Horizon Telescope, Ramesh Narayan, an astrophysical theorist, as is Avi Loeb next to him. Stephen Hawking came to bless and encourage this effort. Xing-Tung Yao was our mathematician. And then on the right, Andy Strominger, one of the great theoretical physicists who works on the combination of quantum mechanics and black holes. And we began to think how we could connect these various disciplines. What would it mean, since the black hole seemed to be of urgent concern to mathematicians, to physicists, to astronomers, to observers, and to historians and philosophers of science? I mean, black holes are unique in that sense. Neutron stars are fascinating to astronomers, but perhaps I'm overstating, but only a little. Mathematicians could not care less about neutron stars. There is no philosophy of neutron stars. They just don't capture the imagination of the many fields, even though they're of tremendous importance in understanding the universe around us. So how are we going to connect the mathematics, the astrophysicist, history and philosophy of physics, and physics itself? Well, one of the great mysteries about black holes was already over a century worked out from the time that Einstein's theory in 1915 was first issued in the midst of the terrible First World War. And on the front lines, on the German side, was Karl Schwarzschild, one of Einstein's close friends. And he took time between barrages of rockets that he was calculating to write a letter to Einstein saying, I have taken refuge from the war in the fields of knowledge that you created, really just a few months before. And he sent Einstein an exact solution to the equations that Einstein had written down in 1915. Einstein was delighted. He went and presented it to the German Academy of Sciences, and it really inaugurated a new kind of exact, not approximate analysis of what Einstein had done. But Schwarzschild noticed that these equations had a very strange feature, one that seemed to be just a curiosity of mathematics, but which turns out to be the guiding point of passage for understanding black holes. For many decades, black holes were considered to just be an artifact of mathematics, a curiosity, but nothing real. In fact, some of my teachers, when I was in college, told me that they didn't think that they were really black holes in the sky, even though they seemed to be quite fascinating from a purely theoretical point of view. There is one black hole in the sky, an enormous one, this one that we made the first image, named after the 18th century French astronomer Messier, and 87th in his catalog. And over the decades, people have studied more and more about the massive galaxy, Messier 87, that Messier had discovered in the 18th century. And with each generation of new telescopes, we could get further in. In 1909, it was seen this huge jet that could come out of it. You kept going closer and closer. Something was happening at the heart of that galaxy, resulting finally in the image that we made of the black hole. And by we, I mean the 200 or so people back in that period leading up to April of 2019, and now a collaboration that spans the Earth that has over 400 members. The black hole at that center is big. It's big enough to, if it was centered at the sun, to include the entirety of our solar system and more. But it's so far away, 55 million light years away, that it's tiny on the sky. It's like trying to image an atom held by your fingers arm's length from your eyes. It required something much vaster than any telescope that had ever been made. It's also difficult to imagine how far 55 million light years is. This is a clip from the film with music by the great composer-performer Zoe Keating that was mentioned a moment ago, and I'll play that bit for you. So what M87 does, or M87 star, the black hole does, is to bend light towards us. It's like the great test that Sir Arthur Eddington presented in 1919, making Einstein the most famous scientist since Darwin and Newton. Only this time, it's not bent by thousandths of a degree, the starlight. The light is bent by a huge amount, and it's that we're able to make a shadow that we could see. So we needed a telescope that was the size of the Earth. Well, no one's going to build us a telescope the size of the Earth. So we had to simulate that to make a virtual telescope by combining telescopes around the world. Now, in the history of astronomy, every time a bigger telescope has been made, vast new things have been uncovered. Newton and Galileo, their telescopes here, had an aperture fraction of an inch or an inch or so. And Galileo was able to discover and understand many aspects of astronomy, from mountains on the moon and the moons of Jupiter and many other things. Newton designed a new kind of telescope, a reflecting telescope. He too made vast discoveries with these tiny tabletop devices. A 100-inch telescope was put at Mount Wilson, which gave us an understanding about the details of galaxies far beyond the Earth. The Hale-Palomar telescope doubled that in size to 200 inches and vastly expanded the size of the universe that we knew in which we lived. The Gran Telescopio Canarias is double that at 410 inches, and the future extremely large telescope will be 1,500 inches. But what we need is something so much bigger than this, you couldn't possibly make it with glass and mirrors. So here's an illustration of how it works. If you had two telescopes that were sitting right next to each other, all they could tell from these two fountains there, if they couldn't see the fountains directly, they just could see the little ripples in the water, was that there was something going on at the center of their little pond. You couldn't tell any details because they're basically getting the same set of waves. If you spread them apart, suddenly you can reconstruct something of the structure of the thing that's far away. Well, that's the idea of the Event Horizon Telescope. We distributed telescopes, or we used telescopes that had been built for completely different reasons over many decades, on 8 telescopes on 6 sites, including 2 on Hawaii, the James Maxwell Telescope and the SMA, both of which were very closely associated with work done here at the Academia Sinica. And then a variety of other telescopes, and we keep adding more to them, including near Grenoble, the Noema, Greenland, and now there are 12 or 13. There's a new set of telescopes in Korea. The array gets bigger and bigger. So as this project got started in 2015, I thought it would be interesting to make a film, not in retrospect, not saying what was it like going towards this, but to film all along the way. And I started filming during this work for the next 5 years. That film is the one that was mentioned, The Black Holes, The Edge of All We Know. It was a huge gamble. I had no idea whether we would eventually be able to see the shadow of a black hole or not. We all had our hopes. I think there were 40 or so people already involved with this by the time I joined in 2015, or 200 by the time the publication occurred. But we could have just gotten a blob. We could have gotten nothing. It really was a gamble for everyone involved in the Event Horizon Telescope, and a gamble to make a film on something that could have been a complete dud. And then in parallel to that, there was another effort by Hawking, Strominger, Malcolm Perry, and young Sasha Heiko, trying to figure out how much information could be stored at the horizon of a black hole. It wasn't clear that that would work either. So I had two hopes and 2 risks in making this. This is a scene, again, from that film. This is the first moment. This is at the Black Hole Initiative, the organization that we formed in 2015. This is in 2018, And this is the first moment that anybody ever saw an image of a black hole.
Okay, which day has the best coverage, by the way? I'm doing 3601 for now.
I was going to do 3601 for now. Same.
Okay, are we ready?
Oh, I'm giddy.
Oh my god, wait, should we close the door? Are we ready?
Wait, what is happening?
We're trying to make an image right now.
Can we just like paste things a little bit?
Alright, well, no, first of all.
Shut, close the door.
That's fine. Oh my god.
Can we start, Michael? You don't have to start.
Wait
for Michael.
Can we just
Going
go on
to
our
be-
little trajectories and, meet up in 20 minutes?
No.
I just think it's like a big moment, and I think for me, I'm not like, I'm just saying like, I think it'd be fun for us all to do the first one together, see the shit, and then go off in our own little ways and fix it. I mean, I think it's just like, it's so exciting that do you want to do it alone?
I would like to see it all together so we can kind of get some idea of the data.
Are you ready?
Ready? I'm ready.
Ready? It's not gonna work at all.
Michael's going to do enhance.
Ready?
Set.
Go? Oh god! Oh my god, we press go!
It's just a waffle. Ah, that looks really, really interesting. How's the waffling going?
Andrews looks beautiful, but there's no tweaking involved.
Because I put compactness very high.
This with a huge.
I think Daniel and I were both getting something like this.
You know, okay.
That's what I get when I use only closure.
Only closure.
Oh my god, look at the chi-squares.
That's pretty good.
And
Coverage. And then this is after a few more iterations, it smooths it out and gets rid of some of the extended junk.
this is on mobile? Or
Wait, but is this only one day?
This is only one day.
You know what?
That's pretty suggestive.
Well, it seems
did you remove these outlines from the other two?
I didn't touch anything.
that is very cool, guys. That is really, really cool. Which one is that?
This is Katie's image.
See, it looks different though, because you guys have a bright spot
On the lower
on
left.
more on this side.
Okay, seriously. but we're all getting kind of aggressive.
Sure,
That's
we all
about
have
the right
it.
size.
So what is the size on that? It's like 40?
This is about 40.
Yeah.
Okay, well, that's what you expect if
See, look.
M87 has 6 billion solar masses.
Yeah, it's a high mass case.
You know what this is? This is a scale to weigh black holes.
Okay, seriously, if we can get anything that even looks remotely like that on all the days.
Guys, the only way anyone's leaving this room is if everybody gets...
So then the hardest thing of all was for scientists to keep their mouths shut for a year and not tell anybody and not show anybody the image. That was the real miracle. The fear was that if it got out and it turned out not to be a real image, to be an artifact, that we would look like idiots and would have damaged the credibility of 200 scientists for the rest of their lives. So it was really important that this not get out. 3 years later, there was a second image of Sagittarius A star, the supermassive black hole at the center of our galaxy. It looks the same size on the sky, but it's like the moon and the sun. They look the same size, but one's a lot farther away and a lot bigger. The M87 on the left is 1,500 times bigger, but 1,500 times farther away. So they look roughly the same. That is to say, they pick out the same size on the sky. Okay, so then the question was, how do you assure yourself, how do we assure ourselves that we were looking at an objective image? So this is something that I've been worried about for a long time, and with Lorraine Daston, who's spoken here a few years ago, we wrote a book called Objectivity about objective images and what made them. So super schematically, in the 18th century, there was an idea that you ought to idealize the things you were looking at. Why would you want to see the sunburnt plant outside my window that's been partially eaten by a caterpillar? You don't. You want to see the perfect form, said the 18th century, of what that would look like. So not only is this skeleton standing up and posing in front of Clara, the Indian rhinoceros, which skeletons don't tend to do, but in addition, Albinus and Van der Laar said that Those things which were less perfect in the skeleton were mended to exhibit more perfect patterns. That was considered to be the ultimate task of the scientist, to show you the reality that lay behind mere appearances. Not this plant, not this not insect, but the Urpflanz, the Urinsekt, as the Germans put it, the originary, the prototype for all of the varieties and changes of things around us. The ideal hand, the ideal skull, the ideal skeleton, the ideal plant, insect, cloud, whatever it was, that's what their goal was in depicting nature as well as possible. In the mid-19th century, something happened to invert that. Suddenly, people began to say, we don't want your idealization or your idealization or your idealization of nature. We want you to transfer what you've seen in the world to the page with a minimum of intervention. We want you, the scientist, to hold yourself back, to self-abnegate, to repress your desire to see some particular form, and instead to depict what was in front of you, this skull or that skull or that skull, not the perfect skull. So when Otto Funke in 1853 looked through his microscope, he knew perfectly well that these blood crystals, which are the transport mechanism for oxygen, he wanted to show how blood transported oxygen, and he crystallized these things. He knew there was no yellow blob on the right there. That was a distortion of the optics of his microscope, but he put it in because he said it was crucial to not intervene. He said, I want to be faithful, conscientious, to depict even the deceptions. If a crystal looked like it was bent, like you stick your arm in the bathtub and it looks bent, he didn't want to depict that as corrected to be straight. He wanted you to show what you saw, to make yourself into a kind of part of the instrument without the desire to perfect, idealize, or confirm your best theories. Schematically, again, in the 20th century, those older forms of image making persist. If you buy a bird identifying book, many of them don't show you a photograph. They show you an idealized version of the bird so you will better be able to recognize it. You can still find atlases of scientific objects that show you things as reproduced as accurately as possible from nature to the page. But suddenly in the 20th century, people begin to say, we need to correct some of these images, not because we're geniuses like Cheselden or Vandelar or Albinus or Goethe, but because we know these instruments and we know distortions that occur. We have to add, as they put it, a certain subjectivity to these charts. We need to use our trained judgment, something we can learn to do. We can learn to recognize a tuberculosis entity, or we could learn to recognize and classify certain kinds of clouds. We can learn to do things with our eyes that help us through expert trained judgment, not because we're geniuses, a separate species of humanity or science, but because we're trained in the art, so to speak. So to schematize this, we begin with truth to nature idealization, where the goal was to depict the metaphysical reality, the reality not that apparent to your eyes, but behind the curtain of appearances. Who does it? A sage or a genius. In the 19th century, you begin to add to that, not displace it, but add to that, and people begin to say, let's remove ourselves and let nature write itself to the page by tracing or photographing or many of the other techniques that were used to do that. And then trained judgment, where you have a trained expert, not a genius or a sage, but somebody who is trained to know when a device is misbehaving and to distinguish artifact from fact. And now we have a new kind of image that becomes more and more important, including for the Event Horizon Telescope, namely the computed image. And we begin to do machine learning, pass-fail tests, neural networks, AI, and the data scientist and computer vision specialist begins to be of ever greater importance in our collaborations. Now, as the telescopes are disported around the Earth, or they exist around the Earth, what we really need is the connection between two telescopes at a time. it's not like making a collage of different partial pictures and then adding them together, but each of these pairs contributes to understanding, like having tuning forks that each pick out a different frequency. If we had enough tuning forks and someone was playing a song in the other room, just by measuring how much each one was vibrating, we could begin to reconstruct what that musical song was. So it is with the Event Horizon Telescope. These different radio telescopes around the Earth make connections, and depending on how far apart they are, they pick out more finer details. And so we begin to construct this, and the turning of the Earth is part of the instrument. It's not just that the Earth is big enough to make this telescope, it's that it has to spin on its axis to change those lengths as seen by the black hole. So then the data come in, and here was a problem. We only have certain frequencies, like a couple of tuning forks trying to recreate what that song was in the next room. And so we had different methods, each one of which was designed to reproduce test images that we sent around to all the different groups. And the different groups then got better and better. We had sort of contests, hackathons, where each of them tried to reproduce the image, including just some random image grabbed from the internet, like the one on the top right there. And each of the different methods tried to reproduce it. And by this time, that looks roughly like that. I mean, it's getting there, at least, for generosity of spirit in evaluating what looks like means. Now, we also wondered, well, could the different groups be guessing what the image really was and tuning to just get that? Well, so we sent around a picture that no one would have anticipated, namely Frosty the Snowman. And so each of the methods then tried to reproduce Frosty the Snowman, and again, pretty close. When all of the methods that we had could successfully reproduce test images, and only then, we distributed the real data to 4 image groups. There's Team 1, the one that you saw the moving image, Team 2, Team 3, Team 4, and here you see many people from associated with Asia A and Academia Sinica. So we had these 4 groups, and we said, whatever you do, do not talk to each other. I mean, Group 1 should not talk to Group 2. Group 2 should not talk to Group 3. Group 3 should not talk. No group should talk to any other group. And now you've got the real data. Make the best image that you can. So when we were working, we would even put up a contact paper on the windows so the other groups couldn't tell what we were seeing. So this is what they got. These were groups 1, 2, 3, and 4. Each of them got images that looked a lot like one another. So that was the first real test here. And we all got together in July of 2018, and all the different groups were assembled in one room, doors closed. Nobody outside the collaboration could hear anything that was being said. And we compared what the different groups were getting, and they, pixel by pixel, and we could see that they were getting something that was very similar. Then the question was, so this is a kind of expert judgment. We said, each group, use your best skills in making an image from the data, the real data. And then we compared them. But then we worried, what if all the groups are imagining the simulations that we've been doing for years and tuning to just get the thing that they expected? Even though the groups weren't talking to each other, what if they somehow unconsciously were all responding to the same imagined reality? So we said to the computer, okay, computer, it's as if you got a computer that could set your camera, what the speed was, how fast, how sensitive the charge coupled device was, what lens was being used, could do all these settings. And we said, computer, vary all these different variables and choose the settings that give you the best reproduction of 4 test images. And it succeeded. It said, okay, well, these are the settings. And then we said, okay, computer, now take the real data, use the same settings that successfully worked on the test data and tell us what you get. So the real M87 data was then sent to the computer. It used those same settings, called them beta, and produced an image that looked a lot like what each of the groups was getting. So this is a kind of not expert judgment, but mechanical objectivity. This is saying just try things, pass, fail. Successfully reproduces the test images or doesn't, until you had a bunch of settings that worked. Then we got together in a big meeting in Hull in the Netherlands, and we had a big debate in the collaboration. And there's a lot of disagreement about this. What are we going to do? We have all these different images from the different groups. Which one are we going to release to the world? Well, people said, what about averaging them? And that was a big, somebody said, yeah, you can't average them. And then that doesn't correspond to the data exactly, and each of these things should be taken separately. But argue, and you say, well, what if Le Monde publishes one image and New York Times publishes another, and it's going to be chaos. No one's going to know what the real image is. So we had this big discussion, and finally we decided that a good argument for averaging was that it would be conservative. It would emphasize the things that the images had in common and de-emphasize the quirky things that one group or another got that nobody else got. So we did that. We averaged these images, and we got this image. And that's the image that was released on April 10th, 2019 in press conferences around the world, including here at the Academia Sinica. What's interesting is that it proceeded using the same steps as we looked at in the history of objectivity, but backwards. Historically, things started with the idealized image, like the skeleton, then went to mechanical objectivity, then went to trained expertise, roughly speaking and schematically again, 18th century, 19th century, 20th century. The EHT did things the other way around. It started with trained expertise, then went to the pass-fail tests run by the computer, and then created an idealized image in averaging. This had a huge effect, this image. It was seen by 1 billion people in the first 24 to 48 hours. It was on the cover of every newspaper in the world. But it was not just in the popular press, it was all over the scientific press. And interestingly enough, I was over at the Museum of Modern Art in New York and showed some of the curators I'd been working with on something else the picture, and they said, oh, we have to have that for the permanent collection of the Museum of Modern Art, and they acquired it, and it's now the first and last time I'll ever have anything in the Museum of Modern Art, along with the other 200 collaborators. So this had a huge effect. And we began to think more about this image immediately. So this was late April 2019. And a group of us at the Black Hole Initiative began to see you could not only see the direct image of light that was bent by the black hole, but light could do a little dance around the black hole. It could go around and then come to us. And if it did that, it would pick out a much thinner, brighter ring called the photon ring. And in fact, if it went around twice, it would get an even thinner, bright ring on the image that we would see on the sky. And at first, this seemed like a pure curiosity. In fact, many scientists thought, well, this would never have any observable consequences, like the black hole itself for many decades. But then we said, well, wait a second. What if we had a telescope that was not Earth size, but 3 times bigger than the Earth? Well, how are we going to do that? We can't pump up the size of the Earth. Well, we could put a satellite up. So in 2019, we began a process of thinking about putting up a satellite and a radio telescope in space, and that's what we're working on now, the Black Hole Explorer, which is, a worldwide collaboration to make what will be the highest resolution telescope in the history of astronomy. Okay, so now back to the Black Hole Initiative. In the Black Hole Initiative, By 2022, so after the publication of the Sagittarius A star supermassive black hole and the M87 black hole, we had this idea of looking for the photon ring with the Black Hole Explorer. The theorists like Andy Strominger and Netta Engelhardt from MIT, who's joined the leadership of the Black Hole Initiative, began to think about quantum holography and to think actually, there may actually be a connection between this deep idea that came out of purely theoretical physics, originally in string theory, but now applied in many areas other than string theory, where what goes on the surface of a black hole, so the horizon of the black hole, actually mirrors in some way the interior of the black hole. And what if the photon ring itself was a kind of holographic image of the black hole? So that led to connections between the photon ring and the pure theoretical physics of holography. The Event Horizon Telescope then, there's a group of people from there and elsewhere started a next generation Event Horizon Telescope where you would work to put more telescopes where we really needed them, not where somebody decided to put $1 billion facility in 1990 or 2000 or 1980 or 70. And so that became a big project. And then this idea that we have simulations of a black hole, which goes from the physics of super highly bent space and time near a black hole out to distances that go past galaxies where it shoots these jets, where general relativity is irrelevant, it's particle physics. You have all these different kind of science from near the horizon, mid-size, out to galactic distances. And these became the 4 leading projects for the Black Hole Initiative, with many connections among them. One of the big tasks is making movies of the black hole. So these were the projects that in 2022, and now it'll go for another 3 years. We were just renewed for another 3 years. Holography, these different scales of simulation, the next generation Event Horizon Telescope, the Black Hole Explorer, and the history and philosophy of science. The history and philosophy of science became very important in many ways. I talked about the way the history of objectivity and objective images came to be part of the vocabulary of at least Group 1, but there are many other things too. To put telescopes in sites became an increasingly contentious subject. The Mauna Kea site, where 2 of the telescopes in the Event Horizon Telescope was shut down for a long time because of disputes between people who lived in Hawaii and were not associated with the telescope and the astronomical community. It was a big battle. It's happened at many other sites. And the historians, philosophers, and sociologists have become increasingly involved in this project to help work out a better understanding between whether it's jobs or recognition of sacred sites or stakeholding groups, including indigenous people that live near these high and dry sites. There were many reasons why this ethical siting, responsible siting, has become a crucial part of astronomy all over the world. And then there are many other topics about the foundations of physics. And the history and philosophy of science is now thoroughly integrated into the scientific work that goes on at the Black Hole Initiative and beyond. So now back to the satellite. The satellite is going to be out at 20,000 kilometers at about an altitude of 12,000 miles. And it would increase the precision of what you see, the resolution, from ground only, sort of schematically indicated over there on the left, to the much finer resolution that you would have with a now 3 times Earth-size telescope. But there are many technical problems, and one of the things that I found completely fascinating is learning to think with the engineers. The engineers have a very different way, and NASA is an engineering organization much more than it is run by scientists. And one of the things that is really distinctive is that if you have a grant from the National Science Foundation in the United States, this is paralleled with other countries as well, and you say, I'm going to find X. You don't find X, you find Y. And Y is really interesting. The National Science Foundation said, great, we're so happy you found Y. It's terrific. We don't really care you didn't find X. You found something else that's great. NASA doesn't think that way at all. NASA says it's like if you came and you said, I'm going to build a bridge over the Hudson River in New York, and you came back and you said, well, there's another great river. The Mississippi is a fantastic river. You would like the Mississippi, and the bridge we built, it's beautiful. In the world of engineering and politics, that's not a success. It's a complete and total failure. So, when NASA says if we were lucky enough to be given an award to fly this mission, if we say we're going to find X, you're judged absolutely and completely about whether you find X. If you find Y in addition, fine, they're happy. But that's like what paint you put on the bridge. It's not, they don't care. But you're making a contract with the government to do something. And that's how they think about something like a space mission. It's a mission. It's like, we're going to go and we're going to retrieve valuable metals from the bottom of the ocean. You either do or you don't. You can't come back and you said, I found really nice fish. So one of the issues is, if you want to we collect petabytes of data. I mean, and for the Event Horizon Telescope, you have to bring it back. You carry it back in these big sealed hard drives. Why don't you send them over the internet? You can't send petabytes over the internet. And you certainly don't have the internet at the South Pole or in Greenland. So you can barely get a little message across, let alone petabytes of data. Petabyte is like the amount in the largest libraries in the world. That's how much information is at the Library of Congress or the New York Public Library. And so we have to send back that much information. Well, you say, why couldn't you compress it? Well, the reason you can't compress it is that the only thing that matters is the overlap between these different telescopes. Most of what's captured by the telescope is junk. Every bit of, it's just a bucket, and light photons are falling into the bucket. You only know what the signal is when you compare two of them. That's why you need these baselines between different telescopes. So how are we going to get this down? Radio won't do it. All transmission of information from space is done by radio, whether it's Elon Musk's Starlink or whether it's James Webb Telescope. And so the big problem for space observations, Hubble Telescope or James Webb, is how do you compress the image before you send it? We can't compress it. So you have to send it some other way. Well, you can do it if you could send things by laser. So everyone knows that laser is the future of communication from space. And a few years ago, in 2022, there was a CubeSat, a little guy like this big, and it was able to send back 200 gigabits per second. That's what we need. Actually, we need a little bit less than that. So one of the big tasks has been to develop and test a laser communication system. There are many things like that where there are major engineering challenges involved in making this work. And then, as the telescope moves around, in its orbit, kind of polar orbit, going around and around, it sends back downlinks to the stations. The minimum we need is 4 ground stations that have little optical telescopes, like they're amateur astronomers that have this size telescope, its aperture like that, and the laser zips down to it and sends this information. It's put on a hard drive, and then the hard drives are collected and put on a supercomputer. And that fills out the virtual telescope, which is what you're seeing on the right here, that allows us to make, we hope, a picture of the photon ring. So the photon ring has 2 aspects, which is really unusual. It's astrophysically interesting because the photon ring's shape, how distorted it is, for example, from a perfect circle, tells you how much it's spinning. And that spin is what drives these huge jets that get shot out and clear out regions of space. They have big effects on the feedback of galaxies and how they form. But it's also physics. The black hole photon ring can tell us much about the nature of space-time itself, something physicists want to know very badly. You could make a historical analogy. The electron was first measured, its charge and its mass, in the 19th century, and then it took a few decades before you could measure its spin. We have a very good idea from the Event Horizon Telescope and from the Nobel Prize-winning work of Andrea Ghez and Reinhard Genzel of the mass of the black hole at the center of the Milky Way, Sagittarius A star. But we've got no direct way of measuring spin, and that's what we could do with the Black Hole Explorer. The faster the black hole is spinning, the more it changes the shape, so that if we could measure the diameter of that shadow, we would actually be able to pin down the spin of that black hole. If we knew the spin, we could say something about jets and how they get generated. It spins up a kind of helix of magnetic fields, and this charged matter gets shot out like pellets from a gun. We would be able, with this much bigger telescope then, to look at other black holes, not just our two nearest and dearest, Sagittarius A star and M87, but many others. So what is it that we're looking at? Well, if the black hole was not spinning, then light could go around it over and over again. Every angle would be like every other angle, and it would pick out a single thin ring that was a single thin shell, and it would look like a pure, thin, round ring on the sky. If, however, the black hole is spinning, then it's like swimming around a whirlpool in the ocean, which is not to be recommended, of course. But if you're swimming with the flow of water, you can come in much closer because it's accelerating you, and you're swimming, you can come right close without falling in, like Edgar Allan Poe's great story about the whirlpool. If you're going against it, you have to be farther away. And so as this spins, the photons pick out complicated orbits and get mixed up, and you have some that are coming very close. You can, to the horizon, you can see some of those, and others, the ones that are going against the spin, have to be much further away. So what this means is that you have some part of the ring very near the horizon and some much farther away. And you can use this so that actually looking at different parts of the ring is probing different regions of space. And that's what the photon ring does. The photon ring is an exploration of space and time near the horizon of a black hole. The horizon of a black hole is an edge of the universe. Anything that happens inside the horizon can never influence anything that happens outside of it. And so the idea that the photon ring is a kind of fingerprint, a kind of marker of the structure of space and time near an edge of the universe is the kind of thing that excites physicists, less so the astronomers. So you can have, in this delicate structure of the photon ring, you can have a measure of how tiny differences in the photon's trajectory could lead one to fall in, one to fly off to infinity, and one to stay just on the edge, the precipice of escape and capture. Here's an animation of that. These are 3 photons that launched almost indistinguishably at the same time and place. And as they separate, as they go, you see them separate. The blue one is subcritical. It doesn't have enough juice, so to speak, to escape or even to stay in orbit, and eventually it falls into the black hole. The red one is on this critical shell and can stay in orbit. And the green one escapes and flies off to infinity, which is good because we need some of them to get to us to make that picture. So those the green ones are the ones that actually will form, we hope, the picture of the black hole. Now, one way of thinking about this is that in a fluid, there's a Russian physicist at the end of the 19th century, had a tragic life, which I won't go into now, but he had this great idea that you could study fluids and look at nearby test particles that you dropped into it and see how quickly they separated. That has come to be known as a Lyapunov factor or exponent, and it tells you about the flow of liquid. But what Einstein taught us 110 years ago, is that light actually travels on the straightest possible line in space, even though space is curved. So if you can see where light goes, like the photon ring, you're actually seeing the contours of the geometry of space and time. So if you imagine light traveling through the universe, it picks out the hills and vales of space-time, and for us in the photon ring, it picks out the nature of space and time right near the black hole. Now there's a further effect, which is really interesting, not something we know how to measure, but that I'm working on with some colleagues, and I find very interesting, which is that there's chaos in this system. If you have, this is just a classical effect that you can see with a suspended little magnet and a magnet on the table, and if you just let it go from different places, say you had 3 magnets on the bottom, what you see is that the magnets, the little plum, will fly around and end up around one or the other of these magnets, even after taking very complicated paths. So it'll end up at 1, 2, or 3, and that's what's thought of as chaos. In fact, if you took different starting points for your pendulum and you marked by color each of these tiles according to whether it ended up at the yellow magnet, the red magnet, or the blue magnet, you would begin to get a pattern. If you continued doing this longer than you have the time or patience for right here, you sped this up, you would actually get a pattern that looked like this on the right, which has this bizarre and fascinating feature that at the boundary of these different areas of the yellow, blue, and the red basins, you begin to see the same kind of image repeated at different scales over and over again. Well, space-time does that too. If you imagine the boundary between those that escape to infinity, those photons that fall into the black hole, and those that remain on orbit, you can make a movie of that, and what you see is that it develops these complicated, self-similar, chaotic patterns, which is really interesting, and not of astronomical significance, at least as far as we know now, but a fascinating insight into the nature of space and time. So you've all seen at these museums of science like a model of a black hole. It looks like a big funnel, and you shoot a little ball, a marble that goes around and around. Well, if you just wanted it to get around once, you could just push it without much attention to the direction. If you wanted it to come around directly and get to the starting point quite precisely, you would have to aim it much more accurately. Well, each of these steps, going around once, going around twice, going around 3 times, requires more and more accurate aiming. And that's why these rings get thinner and thinner as it goes around once or twice or 3 times. Well, our experiment, if we get to fly it, will take this orbit that's at 20,000 kilometers out, 12,000 miles out. If we wanted to see the second ring, we'd have to put a radio telescope on the moon. If we wanted to see the third ring, it would have to be at L2, where the James Webb Telescope lives. That's for the future, but one can dream. We hope to fly our instrument in 2032 to 2034. It's a 2-year mission that we're proposing to NASA in collaboration with Japanese and many scientists around the world. Now, there's a way in which you could think of this purely philosophically, which I think is not something you can do, but it's a thought experiment. If you imagine, say, a person on Earth, and their image, the photon bounces off them and goes to the black hole, or say it starts at some other distant star, and there are people there, and it goes around. When they're a baby, it goes around 3 times and then comes to us. And at the same time, when they're older, a photon from them goes around twice and comes to us. And then, much more recently, there's one that just gets bent by the black hole and comes to us. So we see each of these rings arriving at the same time, but their origins are from 3 different points in history. In a sense, what the black hole is doing is watching the universe and collecting light from wherever light can get to the black hole and storing it in these different rings. The rings contain information like frames in a movie that if you could, against anything practical, but if you could, look into the ring number 1 and compare it to ring number 2, ring number 3, ring number 4, ring number 5, it would be like a movie of the history of the whole visible universe captured around each black hole in the universe. But that's getting ahead of ourselves and deeper into philosophy. In the case of what we actually hope to see in 2032, we want to make a movie of the photon ring because anything that's moving is not photon ring. The photon ring is fixed on the sky. Everything else, the swirling billion-degree gas that's going around the black hole, the stuff that we saw in the first images of a black hole, is not photon ring. The photon ring is not changing. It's fixed. It's fixed by the nature of space and time. So that gives us a movie, gives us actually a kind of scientific epistemic purchase on what's real, what's really photon ring, and what's just a tendril of hot gas. And in that sense, the image carries with it a kind of philosophy built into physics, that the movie of the black hole and all that surrounds it is part of how we can distinguish the reality of what we're seeing, of the hoped-for photon ring, from the artifacts that are circulating around the black hole. The black hole, in other words, collects all these different disciplines, like hot gas around the horizon. Philosophy, history, historical analogies in the way we understand it, the history of objective image making, responsible sighting, and the relationships of astronomy to other stakeholders and peoples that live near those telescopes. It involves mathematics, the details and nature of fundamental physics in the holographic, quantum holography, in simulations, in the new uses of computers to do that, in computer vision, in the future of machine learning and AI, in astronomical observation, all these things over what, in many ways, is the most interesting object in the night sky. Thank you.